In this video, we're summarizing what we have seen in previous video in oxygen nucleophiles. So what are the reactions and how do we predict products? So here, if you have, let's do just acetone, and we're going to make it react with oxygen nucleophiles. So we can form, let's do acetaldehyde. So we can form, if you react with, say, hydroxide, or also water. So different experimental conditions, you can make a hydrate. So say that I do here water and say acidic conditions. Under acidic conditions, you will protonate this first, and then you will have the attack by water, and you will get the product is called a hydrate. So here you will have and I need an extra proton transfer step. This is the final product. So you will have OH, OH, the metal and the H. That was an acetaldehyde. All right, so hydrate. And again, this can be done under acidic conditions or under basic conditions. That was one reaction. Another reaction that we saw is the formation of acetals. So in the acetal formation, we're going to do that under acidic conditions. What you will see when you're completing reactions is, for example, let's do acetone, and I'm going to make this react with an excess of ethanol, and I'm going to have acidic conditions. Under that condition, what is the acid is used to protonate here the oxygen at carbonyl, and then you will have a nucleophilic attack here. A couple of steps because we need proton transfers, but what you form first is an intermediate called hemiacetal. This continues, and after several steps, we will form the final product, which is an acetal. And since the nucleophile has two carbons, right, it's ethanol. So that is the acetal. So if you need help with these mechanisms, I have videos in my playlist. Go check those out for the complete mechanism for acetal formation. What we're doing here is summarizing the reactions. So aldehydes or ketone will react with alcohols to form acetals. That's an intermediate, readily isolated. What is important about acetals? That acetals are stable under basic conditions. And we hydrolyze back to the carbonyl under acidic conditions. In other words, all these arrows, all these reactions are reversible under acidic conditions. See, we need acid in all that. So what that means is that you may have a reaction in which you need to say, what is the product? And you have an acetal in acidic condition. Well, that will hydrolyze back to the carbonyl. So let's complete that. So the whole process with the acetal, and again, taking into consideration that the acetal is stable under basic condition and that can hydrolyze back to the carbonyl under acidic conditions, we can write the following. So we can do these several steps involved the reaction with, say, excess of ethanol under acidic condition, you form the acetal. That is the acetal. And if you start here, you can go back, so that can be hydrolyzed. So we use that in synthesis a lot because we can protect carbonyl compounds, work reactions under basic conditions, and then remove the protection. That's more often used with cyclic acetals. And the idea with cyclic acetals is that you, instead of having, say, 2 moles of the alcohol per mole of the carbonyl, we need, if we have one cyclic structure, let's say, if we're making this react with ethylene glycol, now I have the two OHs, the nucleophiles, on the same molecule. So, and again, the process is reversible. All of the steps, multiple steps, involving nucleophilic attack and proton transfer in dehydration as well. So here you form a cyclic acetal that has this form. So cyclic acetal. So we may have different functional groups in a molecule. We want to protect a carbonyl group. We do this. Is the other reactions we're doing in under basic condition, that's stable, it will stay as is, but then I can hydrolyze back to the carbonyl. That's the use of cyclic acetals. In the only instance in which we saw hemiacetals being, say, isolated, we know about that structure, rarely isolated. So hemiacetals will have OH or R. In the case of sugars, you have cyclic hemiacetals that will have this form. So that is the OR. And you will have a number of OHs, OH, 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 OH. And what I want you to see is that this carbon here has a bond to an OH into an OR. OR is a resonance molecule. So that is a cyclic hemiacetals and sugars. These are more very common in sugars. So that is our summary with the reaction with oxygen nucleophiles. Hydrates, which is the first one that we saw, form easy when we have simple aldehydes. That's a hydrate, OH. That's an hemiacetal, that's an acetal. These are stable under basic conditions, and they hydrolyze under acidic conditions.